We're going to take the same approach, but as we go along the unit circle this time, since we're using sine, I'm looking for vertical distance, or the y-coordinate of each of these points. At 0 degrees, we've gone to the right 1, but vertically we've gone 0. At 30 degrees, this is now the short side of the triangle, the 1/2. Then we're increasing to radical 2 over 2. Then radical 3 over 2 is the 0.87. And then at this point here, our y-coordinate is 1. And continuing, now we're still positive in the vertical direction, but we're decreasing down to radical 3 over 2, radical 2 over 2, 1 over 2, 1/2, and then to 0. Now we're dealing with some negative vertical values because we're going down from the x-axis. A negative 1/2, negative radical 2 over 2, and so on. 300 is the last point on our table, but we can see the repeating patterns that the next one would be a negative radical 2 over 2, and then a negative 1/2, and so on. We're going to plot these points now, graphing theta and sine theta. Here's our first point at 0, 0. Now we're seeing the same values as we did in the cosine function, so we're going to have a very similar shape, but we should understand that the sine function crosses through the origin, but the cosine function crossed through the point 0, 1. That's a helpful way to keep the two graphs distinct, because otherwise they have a very similar appearance. Here we're finishing up the points beyond what we have in the table, including a negative rotation. Because it's working same way as cosine, we can use negative values. And connecting those points, there is our sine graph. It has the same shape, but it's crossing through the origin, where the cosine function crossed through the point 0, 1. Let's talk about this repeating pattern we first referred to in the cosine graph. We're calling this one period, and a graph that repeats, has one piece that repeats over and over again, is a periodic function, or a periodic graph. We're interested in identifying how far we have to go to be able to see one complete cycle. If we started at 0, at an angle of 0, we increased, we got back down here, we hit 0 again, but it's not a complete cycle because we didn't catch the part where we have the negative values. But once we get back to 0 here, now we have the part repeating again. So it took 360 degrees, or 2 pi radians, for the period. One strategy that people will use for measuring period is that we can go from peak to peak. If you go peak to peak, you're going to find a period that way. You don't have to be concerned about, well, I'm at 0 again, is it really the entire period? I mean, it's not too crazy to have to see, but peak to peak is another strategy we can use, and it will give us the same result, 2 pi, or 360 degrees. Here's a computer-generated graph of cosine. We can see this wave form, and we can see the period here. It's 2 pi. Starting at 0, 1, we go down to negative 1, and then back up to positive 1, and that covers, there's 90, 180, 270, 360 degrees. Let's take a look at the sine function. Same shape because we saw those same function values, 1/2, radical 2 over 2, radical 3 over 2, and so on. But our initial point was at the origin, 0, 0. We still see the period is 2 pi, and we have this repeating periodic function. Here are those two graphs side by side. We can see that one is just a result of a horizontal shift by how many degrees? 30, 60, 90 degrees. Shifting the graph by 90 degrees can get you from a sine to a cosine if you shift to the left, or from cosine to sine if you shift to the right. While we're at it, we should take a look at the tangent graph and see this interesting shape. So let's construct this. We're going to start off by remembering these values on the unit circle, but when it comes to tangent, we're not interested in these coordinates x or y. Coming back to this unit circle diagram, and let's recall what our main x and y coordinates were here in quadrant 1. At 30 degrees, 45 degrees, and 60 degrees, we had these values of cosine and sine. Now tangent can be defined as sine over cosine, so I can just simply do my sine value over cosine value and see what that result is to come up with tangent. But that's doing a lot of division with fractions, or even worse with these decimals. But let's break down some important things to know about tangent. Remember this formula for calculating slope, y2 minus y1 over x2 minus x1. Now we're going to pick some random point on the circle. It's down here, and we know that our x and y coordinates on the unit circle are cosine angle and sine angle, and it's the angle caused by rotating from 0 degrees counterclockwise around to this point here in quadrant 4. I'll now think about a segment from the origin to this point, and at the origin we know that coordinate is 0, 0. If I choose to use the origin as my x1, y1, and cosine theta, sine theta as x2, y2, and put it into the slope formula to calculate the slope of this line, it becomes sine theta minus 0 over cosine theta minus 0, and that's sine over cosine, that's tangent. So we can think about tangent as a slope of the line that goes from the origin to the point on our circle that corresponds to some angle rotation. And since our x-coordinate is cosine and y-coordinate is sine, we will use y over x to calculate tangent. Now let's talk about making life easy when it comes to dividing these fractions. First, our slope at 30 degrees, y over x would be 1/2 over radical 3 over 2. We've got a complex fraction. We could simplify it in a few different ways. You could take the second fraction, flip it and multiply because we know this big fraction bar is a divide. We could multiply numerator and denominator by 2, absolutely. What I want you to really recognize, though, about complex fractions is if ever these two denominators are the same, they basically cancel each other right out. And definitely those two methods I described will show us that very same result, but it can be a quick way to show that this is just a 1 over radical 3. Lose both of those small denominators of 2. Now let's rationalize the denominator, multiply top and bottom by radical 3. We get a result of radical 3 over 3. And for a decimal approximation, about 0.58. At 45 degrees, y over x, that's the same numerator and denominator, it equals 1. Or perhaps you even remember from first learning about slope that a 45-degree angle is a slope of 1. Next, at 60 degrees, slope y over x, we have a radical 3 over 2 over 1/2. Again, I'm losing those denominators of 2. It's a radical 3 over 1, or just radical 3, approximately 1.73. So these quantities aren't too difficult to memorize. Radical 3 over 3, and then the radical 3, and we'll know at the diagonal 45, 135, 225, 315, those all will have a slope of positive 1 or negative 1. And here, what I like to think about is, here's radical 3, and here is radical 3 divided by 3. So it's a smaller value doing that divide by 3. And I know about slope that the steeper the line gets, the higher the number is for slope. So the radical 3 is going to end up being where I have steeper lines. The radical 3 over 3 is where we have lines that are not as steep as the other ones. Let's fill in slope for our other points here. A pure horizontal line has a slope of 0, and a vertical line has a slope that is undefined. To come up with tangent for these other values, we're not interested in reflections because, again, it's not about the x and y coordinates. It is about slope. The first thing we could say is the slope of this line that goes from the origin to radical 3 over 3 through 30 degrees, it's going to have the exact same slope as a line that comes backwards this way into quadrant 3. It's one solid straight line, so if the slope up here is radical 3 over 3, the slope down here is also radical 3 over 3. So knowing quadrant 1, we automatically know quadrant 3. Slope of 1 at 45 degrees, so all the way back here at 225, it still has slope of 1. And here at 60 degrees, the slope is radical 3. Follow it all the way through the origin down here to 240 degrees would also have a slope of radical 3. Now what about quadrants 2 and 4? Let me start with quadrant 4 actually. Talk about the slope right here. If I haven't memorized that this not so steep line is a slope of radical 3 over 3, because it's going uphill, it's positive, then that same angle but going downward is the same kind of steepness but downhill. So it's still radical 3 over 3, but now it is negative. That's how I'll know about the tangent values in quadrant 4. So right here, downhill at negative 1, and now the steeper line here, it's going to be negative radical 3. And now when it comes to Quadrant 2, I'm just following these all the way back. So here is a negative slope. It's not so steep, so it's the negative radical 3 over 3. Here it would be same slope down here, negative 1. And at this point here at 120 degrees, that follows all the way down to this, not that one, to this point right here, a slope of negative radical 3.